Nick, my friend, what are the 3 laws of static charge? I'm going to give you a hint with the first one. The first one, I'm going to put the word like. Oh, lie. Like charges, repel. Then I'm going to put the word unlike. Unlike charges, attract. And then what am I looking for here? Neutral charges are blank to blank objects. Attracted to both. Because of that, that's the balloon illustration that I showed you, where you saw the charges inside the wall just separated. You didn't actually change the number of positive and negatives in the wall, but you could move them around, and that's why a neutral charge was attracted to anyone. We need to get a little technical here, Brooke, when you're done yawning. We have 2 types of forces. The first type of force is what we call a contact force. And in a contact force, objects must be touching. Objects must be touching. Here is the very, very basic contact force. If I want to apply a force to Drew, I can either do that, or I can use an intermediary. I can touch him with a second object, where we would call that a contact force. I don't know if you noticed, but that's not what was happening with some of the electricity stuff I was showing you. Remember when I rubbed that piece of plastic and then I made the paper jump to it? You might have seen, if you watched Close Mason, the paper, the ruler, the plastic, never touched the paper. The paper jumped. The plastic exerted a force on the paper without touching it. Is that witchcraft? No. We have to have a special explanation for that, though. Otherwise, it would be witchcraft. We call these action at a distance forces. And this is when you act on an object without touching it. Now, I gotta be honest here. Sierra, as a physics nerd, I have a bit of an issue with the way your Science 9 textbook phrases this. And I'm gonna go on a rant later on. It's not gonna be in your notes, because I am gonna teach the Science 9 curriculum the way the textbook wants. But I'm going to try and say to you, technically, this is really how we think about it in physics. So, what's an example of an action at a distance force? Magnets. Do you have to touch magnets together before they exert a force on each other? No. And in fact, if you have the magnets opposing each other, you can't touch them together, but you can feel you're trying to push them closer and closer, and they won't go together. You guys have tried that before, right? Oh, and another example of an action at a distance force is electric forces. 2 positive objects repel each other, but there is no contact. Another good example, magnets. Another example of an action at a distance force that you all take for granted is gravity. How many of you ever jumped off of a diving board into a swimming pool before? Is the earth touching you while you're in the air? No. Is the earth still exerting a force on you? What do you think's pulling you down? Okay. How does this work? So I said that there was 2 ways that I could exert a force on Drew. The first way is by pushing him. I'm having fun with this one, sorry, Drew. Or I could have an intermediary, in this case the meter stick. Okay? Well, it turns out, and this is why I have an issue with the way the textbook phrases this, I actually would argue that the earth is touching you while you're in the air, but it's touching you the same way that I touched Drew with the meter stick. It's touching you with something that's invisible that you can't see. Wait a minute, Mr. Dewitt, that does sound like witchcraft. No, we've thought about this very, very deeply. Or 2 magnets actually are touching each other, Trevor. Even though they're not physically touching, they're touching each other with an invisible thing that you can't see, but it's there. We have a name for this invisible thing. For electricity, we call it... Oh, my pen stopped working. Try this again. An electric field. For gravity, we call it a gravitational field. For magnets, we call it a, take a guess, magnetic field. There is a whole branch of physics called field theory that says, you know what, really we can't have action at a distance forces. There has to be something in between them that's interacting. And there is. It's just invisible and you can't see it, but you can feel it and detect it. I'm going to go on a bit of a rant for that. Mr. Dewick will now go on a Physics 12 electric field action at a distance rate. Not on test, but cool. I'm even going to pause the video here for a second. But it's kind of cool. I have a sim here, I think. Charges an electric field, yes. Have to wait for it to run. Come on. Sorry, it's here we go. I agree and continue. So here's a positive charge. Dunk. No. That's what we see because our eyes only see a very thin band of light. If you could see the entire spectrum, if you could see electric fields, Nick, what you would really see is that. You would see an invisible, like the tentacles of an octopus, electric field going out in all directions, and you would see, Cole, that the further away you got, the weaker it would get. But if I put a negative, these are unlike charges. Nick, unlike charges what? So if I put a negative here, it would feel, I've got it frozen, but it would feel a force pulling it here, and the positive would feel a force pulling it towards the negative. How? Those fields are what's transmitting the force. Believe it or not, Brooke, that's how radio works. What? Yeah. Radio, we take a very, very strong electric field done through some kind of machinery. Did I tell you, Josh, that the electric fields extend all the way out to the edge of the universe? I did. We don't need them to extend to the edge of the universe for radio. We just need them to extend fairly strongly for 50, 60 kilometers. So here's how it works. At the radio station, they generate a changing electric field, and I can do that by wiggling this electron. That changing electric field goes to your radio antenna back home, and if I, let's even turn on the electric field line there. Wiggle my radio wave. Can you see very faintly back home that little electron, that the charges inside the radio are also oscillating in sympathy, very slightly because it's far away? Let me make it bigger. Oh, you know what? Instead of doing it manually, there. Now, there's two types of radio stations. What are the two types of radio stations? What M and what M? Okay, AM stands for amplitude modulated. The amplitude is the height of the wave. That's an AM radio wave. And by changing the different heights, your radio can tune into the different stations. Oh. Let's go back to the middle here. FM stands for frequency modulated, and that's how many waves per second, not the height of the waves, but how many waves per second. There's an FM wave. There's an FM wave. And all your radio does is it translates those oscillations, sorry, let's make the frequency a little faster. It translates those oscillations into sound on the other end. Okay. Big deal? Okay. This is how gravity works. All right. So, let's go back to electricity. Am I recording? I am. Good. It says, add the appropriate force arrows. Nick, these first two charts, yeah, I'm going to keep coming back to you. Like or unlike? Unlike. Attract or repel? Attract. So, the positive will feel a force that way. The negative will feel a force that way. That's what I mean by force arrows. I might ask you to draw a little force arrow diagram on your test as well. Gonna make it, Brooke? Okay. Nick, like or unlike? Like. So what can you tell me about those? So I think for here, the force would be that way and that way. By the way, this is also nice because now this gives us a way to move stuff without touching it. If you don't think a lot of our machines and remote control toys and all that stuff take advantage of this, you're nuts. Although actually we do most of it using magnets because magnetic force is easier to control, but still the same idea. Like or unlike, Nick? Yeah. So, I'll change colors. Now, we're going to pretend that these are three completely separate diagrams because also, technically, if those were on the same page at the same time, then, Jaden, these two would attract each other, these two would attract each other, these two would attract each other, these two would repel each other, this and this would repel each other, but this and this, it would get very complicated. So I'm not going to ask you to do a big funky charge diagram, probably two charges. I might ask you to draw the forces on them. What if you had more charge? Do you think if you had a bigger charge, would that make the force bigger, smaller, or stay the same? What do you think? Big, yeah, because if one charge is exerting a force, two charges would be twice the force. Three charges would be 3 times the force. So more charge equals bigger force or more force, stronger force. Now, what if we move the charges further apart? Do you think the force would be bigger, smaller, or stay the same? Smaller? What if we move the charges closer together? Bigger, smaller, or stay the same? And this is, those of you that were playing with the Van de Graaff, this is some of what you noticed. This is also why when you gave each other daps to get the shock, you had to get close enough for the force between the charges to be big enough that they could jump the gap. So decreased distance, bigger, stronger, or stays the same? Sorry, bigger, small, stronger, weaker, or stays the same? Say it out. I heard someone say it. Yeah, say it loud. Stronger, loud and proud. Yeah. So it turns out this force between electrically charged objects depends on two main things: the distance between them and how much the charge is, how big the charge is. The direction depends on like, repel, unlike, attract. Okay. Oh, here you go. I filled it in. In fact, can you bring the south poles of two strong magnets together? If you've ever had very strong magnets to try and push them together, it's impossible. The closer you get, in fact, the force actually shoots off and starts to approach infinity, and you can't push them together. So we're going to do a short little lab. So some good learning in that little electroscopes lab. Here's our terminology for today. There are two main methods of charging objects: conduction and induction. Conduction and induction. Charging by conduction. What am I looking at here, Mr. Dewick? When a negatively charged insulator touches the neutral object, the electrons from that negatively charged insulator flow into the object. That neutral object has just gained electrons. So you can remember the electroscope. You made the rod negative, and then when you touched the electroscope, the leaves moved apart because they became negatively charged. There's a lovely picture on page 259 in your textbook if you want. Oh, yeah, here. Okay? This is what was going on when you came in contact. A negatively charged rod actually physically adds extra electrons to the electroscope. Oh, and by the way, that's why you have, if you notice, that little plastic ring around the metal, because that plastic ring insulated the foil from the rest of the metal chassis so that it wouldn't get grounded into your desk. What would happen if you touched a neutral electroscope with a positively charged object? Nothing. The leaves would repel each other, or the leaves would attract each other. You know what? We're going to vote. How high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Dewick will make fun of me if I don't vote, and he will. I'm positive. Pretty sure. I'm only voting because Dewick will make fun of me. So, supposing instead of touching a negatively charged object to the electroscope, we touched a positively charged object to the electroscope. Who says, Mr. Dewick, nothing will happen because it's positive and so nothing will happen? Who says they're going to repel each other, Mr. Dewick? They're going to repel each other because something, I don't know, like repel. Okay. Who says they're going to attract each other? They're going to attract each other. Who didn't vote?
I don't know.
That's not an option. That's not what I gave you. Which one? Second one? So then I always go like this, Matt. I tell my students, convince me. You can either attack someone else's answer as being wrong, or you can defend your own answer as being right. Attack or defend. Convince me. Give me an explanation. What do you think? Give me 1 second, by the way. I'm going to pause the video. Well, let's draw a picture. Here's the foil. Yeah, Brooke.
If it's like a positive charge and you're bringing it to neutral, the negative charges go away.
Ah.
The positives.
So right now I have this, and then you're telling me when I touch, a bunch of negatives would flow from the foil onto here. What would that leave the foil's charge as then?
No. Like,
You were right. Okay, keep going. You were great. Keep going. So if a bunch of negatives flowed from here, if these lost electrons, because those electrons flowed onto there, because unlike attract, what would be left behind here? Extra what? Extra positives. Now, it's not going to be totally positive. There's going to be still some negatives, but it's going to be, the net is still going to be positive. And then, Nick?
like charges were
There it is. The same thing would happen, except it would be the positives left behind that are repelling each other. So option 2 is right. Same result. Electrons from the leaves would move into the positively charged object, leaving the leaves with a net positive charge, so the leaves would move apart from each other. Keep going. Mr. Dewick's dumb way to remember, conduction needs contact. Oh, and for what it's worth, induction is indirect, which is my word for no contact. Okay? I am going to probably ask you a question about the difference between these two on your test in some way. Pith ball demonstration. You always have to say that very, very carefully. A negative, well, let me show you. Pause the video. We're going to finish off drawing a little picture here. So, you ready? I'm going to make this nice and big. How about 300? There we go. So here's my stick figure diagram of what we just saw. So I started out with some extra negatives there, but the ball was neutral. So to show that the ball is neutral, I'm going to put 2 negatives, and I'm going to put two positives. Now, please understand, in real life, it's trillions of negatives and trillions of positives, but these are charge diagrams. We're going to just simulate what's going on. So, initially, we get some attraction. Why? Well, right at this situation, do I have touching twice, I think? I hope? Yeah, I do. Good. So, the initial attraction, this is negative. In the ball itself, what really happens is the positives get pulled here, the negatives get pulled here. Now, Nick, the ball is still neutral, but this is why neutral objects are attracted to anything. Inside the neutral object, we're moving the charges around, the electrons are getting repelled, and that leaves a positive section closest to the negative rod. That's why it attracts. By the way, those of you that had the best view, you'll notice the attraction was not as strong as the repulsion. The repulsion was much stronger. Okay. Then, charges jump. So we have negatives. What's really going to happen here is some extra negatives are going to jump. And we have the positives, and we have those original negatives. We're going to end up with more negatives on that ball because there's so many negatives on that ruler that they can repel each other and overcome the ball's reluctance to gain extra electrons. And so now, what's the charge on the ruler? Still. Negative. What's the charge on the pith ball now? Now it's negative. And so now, Nick, are you ready? We have like charges, and so we repel. So I'm drawing 4 negatives and 2 positives as my analogy. Is that okay? Yep. Good explanation? So, you know what? I think I'm going to do this. I got 7 minutes. I can bring out my magic toy.